Book 1. Tectonic Processes and Hazards. Enquiry Question 1. Part 1. The Structure of Earth. The Earth is made up of different layers, and it is important to know the name and description of each one. Asthenosphere. It is the surface layer of the Earth composed of the crust and upper mantle. It is broken into tectonic plates which constantly move. Mantle. The thick, mostly solid, layer of rock located between the crust and the core. It is here that convection currents are found in areas of higher temperature. Mesosphere. This is the upper portion of the mantle consisting of rocks which are brittle enough to break under stress. Lithosphere. It is the rigid, outermost layer of Earth, made up of the crust and the upper mantle. Inner core. The inner core is hot and dense because pressure prevents melting. It consists of an iron-nickel alloy and has a radius of about 1,220 kilometers. Outer core. This is a fluid layer between the solid inner core and the mantle. It is mostly made up of iron and nickel. Part 2. Plate boundary types. There are three main types of plate boundary. You should know the nature of each and which processes they cause. It is also important to note a case specific for each type to help in exam answers. Convergent or destructive plate boundary. Here two plates move together and the most dense plate is subducted and melts into the mantle. At this boundary type, earthquakes are the largest and most damaging as stress builds in the subduction zone. Convergent boundaries create a large proportion of the Earth's active volcanoes and the most explosive types. These tend to be less frequent but more destructive. Some case specifics for convergent plate boundary locations are the Japan 2011 earthquake and tsunami, the Nepal 2015 earthquake, and the Pinatubo eruption of 1991. For more information on these, see my case study series, which contains the key information you should include in your answers. Conservative plate boundary. This is where one plate slides against another, and lithosphere is neither created or destroyed. Conservative plate boundaries create shallow focus earthquakes that can be very destructive. They do not cause volcanic activity. Case specifics include Los Angeles 1994 earthquake and the Christchurch earthquake of 2011. Divergent or constructive plate boundary. Here two plates move apart from each other. This leads to the creation of crust and is most clearly displayed at mid-ocean ridges. The earthquakes created are frequent, low-risk seismic activity, which do not normally cause tsunamis. Rift volcanoes are created which are usually less explosive and more effusive, especially deep underwater. Case specifics to note are the 2002 Mount Nyiragongo eruption and the Mid-Atlantic Ridge. Part 3. Plate tectonic theory. The next slides explain plate tectonic processes you need to understand. Firstly, convection. Heat is produced by the decay of radioactive elements, meaning areas of the lower mantle are heated. These hot liquid magma currents circulate in the asthenosphere, meaning that the tectonic plates are moved. Slab pull. Newly formed oceanic crust is denser and heavier once cooled. As a result, it sinks into the mantle under its own weight. Consequently, the rest of the plate is pulled down. Subduction. This process counters seafloor spreading by destroying crust. One plate moves under another and melts in the mantle. This area is called a subduction zone. Seafloor spreading occurs where magma is forced up from the asthenosphere and hardens. The new crust forces plates apart. A key term to understand is paleomagnetism, when rock forms from lava the minerals align with the Earth's polarity. This changes about every 400,000 years so patterns form. Part 4 covers the previously discussed plate boundaries in more detail. There are 6 types of plate boundary that you need to know about. Convergent plate boundary, oceanic and continental. Two plates move towards each other creating a destructive plate boundary. The denser plate subducts under the other and melts. Key features include deep ocean trenches, volcanic arcs, fold mountains, earthquakes and volcanic eruptions. Convergent plate boundary, oceanic and oceanic. Two plates move towards each other creating a destructive plate boundary. The denser plate subducts under the other and melts. Key features include deep ocean trenches, island arcs, submarine volcanic activity and earthquakes. Convergent plate boundary, continental and continental. Two plates move towards each other but neither subducts. The plates fold and uplift. Key features include fold mountains, no subduction, earthquakes and an ongoing uplift. Constructive plate boundary, oceanic and oceanic. Two oceanic plates move apart. Magma rises to fill gap and new oceanic crust forms. Key features include mid-ocean ridges, volcanic activity and earthquakes. Constructive plate boundary, continental and continental. Two continental plates move apart creating a rift valley or volcano as the crust stretches and thins. Key features include rift valleys, volcanic activity and earthquakes. Conservative plate boundary. Two plates slide past each other horizontally. As a result, friction and stress builds. Key features include strike-slip faults, earthquakes, but no volcanic activity. Part 5. Volcanic hazards. There are 7 main volcanic hazards to be aware of. These are pyroclastic flows, ash or tephra, lava flows, lavas, volcanic gases, tsunamis and jokulorps. Pyroclastic flows. A pyroclastic flow is a fast-moving, destructive current of hot volcanic gas, ash, and rock fragments that move away from a volcano. They can be as hot as 1000 degrees Celsius. These are most hazardous at ground level. They are caused by the explosion of bubbles of molten magma in the volcano. Ash or tephra. These are materials ejected into the atmosphere during an eruption. It can vary in size, for example bombs which are more than 32 mm in diameter. It can cause roofs to collapse and can impact air travel. Lava flows. This is a flow of lava away from a volcano. It can be very dangerous if fast-moving. The viscosity is determined by the amount of silicon dioxide it contains and impacts the speed at which it travels. Lavas. These are volcanic mudflows, composed of silt and sand. It is secondary hazard brought on by rainfall mixing with materials ejected from the volcano. Volcanic gases. This is a hazard associated with explosive eruptions. The gas clouds are normally made up of water vapor, sulfur dioxide, hydrogen, and carbon monoxide. It can lead to acid rain, which has many environmental, social, and economic impacts, which you can consider in answers. Tsunamis. When a huge volume of water is displaced at once, forming massive, destructive waves. This is a secondary hazard. This process is explored in more depth later on in the video. Jokulorps. This is a glacial outburst flood. They occur when a lake fed by glacial meltwater breaks its dam and drains suddenly and catastrophically. Part 6. Hotspot volcanoes and mantle plumes. In this part 1 we'll quickly cover the topic of hotspot volcanism and mantle plumes. A hotspot volcano is one that does not form at plate boundaries. It is formed as a result of a volcanic hotspot, an area in the mantle from which heat rises from a hot thermal plume deep in the earth. The crust is melted away and magma rises through the cracks to form active volcanoes. The hotspot is stationary, so as the tectonic plate moves away, island chains form over extended periods of time. An example of this is Hawaii. As you can see below, the islands form in a chain leaving extinct volcanic islands behind the active one. Part 7. Earthquakes and tsunamis. In this part we will cover the cause of an earthquake, seismic waves, secondary hazards of earthquakes, how tsunamis form and factors in how impactful these are. The sequence below shows how an earthquake occurs. Tectonic strain builds gradually, which stores elastic energy in crustal rocks. When the pressure exceeds the strength of the fault, the rock fractures. This produces the sudden release of energy, creating seismic waves that radiate away from the point of fracture. The brittle crust rebounds either side of the fracture, which is the ground shaking. The diagram below shows the anatomy of an earthquake. Fault, a fracture in the rocks that make up the Earth's crust. Epicenter, the point at the Earth's surface directly above the hypocenter. Hypocenter, the point within the Earth where an earthquake rupture starts. The first type of seismic wave is a P wave, also known as a primary wave. The vibrations are caused by compression. They spread quickly from the fault at a rate of 8 km per second. They can travel through liquids. S waves, or secondary waves, vibrate at right angles to the direction of travel. Move at 4 km per second. They cannot travel through liquids. L waves, or love waves, are the final type of seismic wave to know. Vibration occurs in the horizontal plane. They are high amplitude and cause the most damage. Secondary hazards of earthquakes. The first hazard we will look at is soil liquefaction. This is a natural hazard that occurs when soil loses its strength and stiffness and behaves like a liquid in response to an applied stress, such as an earthquake. This can cause major damage to buildings and other structures. Soil liquefaction occurs when waterlogged, loosely packed sediments at or near the ground surface lose strength due to strong ground shaking. The 1989 Loma Prieta earthquake in California is an example of an earthquake that caused this. Another hazard is a landslide. These are common in mountainous areas such as Nepal. These flows of material can travel many miles, causing damage to property and the environment. How tsunamis form. A sudden shift in plate movement causes water displacement at the epicenter. Large waves move along the seabed away from the epicenter. As the waves move from deep water to shallow water near the coastal area, they increase in height and break. Factors affecting the impact of a tsunami. Below is a list of the factors you should consider. The duration of the tsunami. The wave amplitude. The depth of the water. The gradient of beach. Night versus day, this impacts the number of people out. The level of development. Strength of infrastructure. Warning systems and how much notice is given. The last part of this video will cover the features of effusive and explosive volcanic eruptions. The table below shows the features of effusive and explosive eruptions. In short, explosive eruptions produce huge amounts of material, which has a major impact. These are the types of eruption that produce huge ash clouds and can cause international problems. For example, air travel. Effusive eruptions result in the outpouring of lava onto the ground because it is low viscosity. Enquiry Question Two. Why do some tectonic hazards develop into disasters? Part 1. Natural hazards and disasters. To start this video, it is important to understand the definitions of these key terms. These are used throughout the inquiry question and you must know their meanings. A hazard is a perceived natural event that has the potential to threaten both life and property. A disaster is the realization of a hazard that causes a significant impact on a vulnerable population. Vulnerability is the ability to anticipate, cope with, resist, and recover from a disaster. And finally, resilience is the ability to protect lives, livelihoods, and infrastructure from destruction, and to restore areas after a natural disaster has occurred. As we will see next, it is important to understand that a disaster only occurs when a vulnerable population is exposed to a natural hazard. The model here is called Degg's model. It is a useful way to visualize the theory that a disaster only occurs when a vulnerable population is exposed to a hazard. You may notice how it looks similar to a Venn diagram, and you should remember this model, as you may be asked about it, or asked to give an example of a disaster model. Continuing with this theory of disasters, we can now see the hazard-risk equation. It means that the geophysical event that poses a threat is multiplied by the social group that is at risk. This means that the hazard is made worse by vulnerability. However, this equation illustrates how the capacity to cope can reduce the risk posed by the hazard. Capacity is the country's ability to withstand and manage the hazard event. This equation can be used to differ between two disasters and understand why they may have been different. For example, the Nepal earthquake of 2015 had a similar magnitude to the New Zealand earthquake of 2016. but 9,000 people died in the Nepal earthquake, compared to just 2 in New Zealand. We can recognize how, as a high-income country, New Zealand reduced the risk through its capacity to cope. To conclude this part of the video, we will look at the pressure and release model. It is another way to illustrate the link between vulnerability and disasters. You will notice how it is much more detailed than Deg's model from earlier. But it used the same theory. As you can see, vulnerability is shown as being dynamic and progressive. Within the pressure model, there are 3 sections of vulnerability. These are root causes, the existing core issues; dynamic pressures, influenced by root causes, and change because of this; unsafe conditions are factors that can make a disaster significantly worse. These factors are created as a result of the previous 2 categories. They cannot improve without deeper societal change. In this part of the video, we will be looking at tectonic hazards, how they are measured, and how they are profiled. Firstly, we will look at the scales used for tectonic hazards. This is the Richter scale. It is used to measure the severity of earthquakes on a scale from 0 to 9. It is a measurement of the amplitude of the waves produced by an earthquake. It is an absolute scale. This means it will be the same wherever the earthquake happens. This is the moment magnitude scale. It is a modern measurement used by seismologists. It describes earthquakes in terms of the energy released, as you can see on the diagram. It measures the magnitude of an earthquake based on its seismic moment. The final scale for earthquakes is the Mercalli scale. This measures the experienced impacts of an earthquake. It's based on the observable damage caused by the earthquake, which can be subjective. The Volcanic Explosivity Index is a scale used to measure the size of explosive volcanic eruptions. Volume of products, eruption cloud height, and qualitative observations are used to determine the explosivity value. On this diagram, you can see the Mount Pinatubo eruption of 1991. This is an essential case study to know, so make sure to watch my 5-minute summary on the event. Here you can see examples of hazard event profiles. Hazard event profiles compare all of the physical processes shared by hazard events. They help governments decide which areas most money should be spent on to improve resilience. They are useful for comparing 2 earthquakes to each other, if similar metrics are used. However, when comparing earthquakes to tsunamis or volcanic eruptions, they may not be as simple to read. This section will look at links between development and vulnerability. Firstly, the development-disaster relationship, as shown on the diagram. You should understand this relationship and be able to explain the factors involved, both economically and socially. Disasters can create development opportunities. In the wake of disasters, decision-makers can be more willing to make changes, knowing that it is necessary to protect the population. This development will include disaster risk measures and reduce vulnerability for the future. Disasters can also destroy development. Physical assets are destroyed, causing a loss of production capacity, market access, and input materials. Damage is dealt to infrastructure and livelihoods. The features of disasters that cause this can be revised using my Enquiry Question One summary. Importantly, the workforce can be weakened. This damages and limits development and can become a longer-term issue if labor shortages cannot be reduced. Development reduces disaster risk. Resilience is increased by improving living conditions. These include drinking water access and high-quality infrastructure. Poverty can be reduced using fair trade and technology, reducing vulnerability. Development can cause disaster risk. Unsustainable development can create unsafe working conditions and degrade the environment. Development can generate inequality and result in vulnerable members of society. This is the risk-poverty nexus. The risk-poverty nexus model shows the strong link between poverty and the impacts of a hazard. Those in poverty are the most impacted by disasters and remain in poverty because of the disaster. Their ability to recover and reconstruct after a major disaster is often limited, further diminishing their ability to increase resilience to disasters. Similar to the pressure and release model, there are underlying issues which fuel this issue. Examples of these issues are weak political organization, political corruption, and uneven economic development. The characteristics of a natural disaster are influenced by human and physical factors. Development plays a major role in this. Low-income countries can see huge impacts if a disaster occurs, as a result of their infrastructure being weak and unable to cope. Let's look at some factors that influence this. Developed countries suffer higher but short-term economic losses, whereas the social and economic impacts are far more long-term in developing countries. Poorer people in developing countries are often marginalized socially, politically, and geographically, meaning they may not receive early warnings on the hazard, increasing their vulnerability. More developed countries also tend to have early warning systems, whereas developing countries may struggle to afford this technology. Financial resources, effective governments, and strong community links are all required for early warning systems, well-organized evacuation procedures, seismic-proof buildings, and protective barriers. On a local level, inequalities have the following impacts on hazard impacts. Poorer countries have disproportionately higher mortality and economic loss risks. Countries also have a particularly low resilience to these losses. Disaster losses can lead to major setbacks in their economic developments. At a local level, poorer areas still suffer disproportionately high levels of damage in disasters. This is related to factors such as unsafe housing. People living in these poor areas have little resilience and are very vulnerable. Expansion of informal settlements in hazard-prone areas also increase the risks. Lack of structure discourages planners from investing in the area. This leads to an even larger wealth gap. To look at how governance impacts natural disaster impacts, let's take a look at the Haiti earthquake of 2010. Haiti's poor governance significantly worsened the impact of the 2010 earthquake by failing to prepare adequately for natural disasters and lacking effective response systems. The Haitian government was plagued by political instability, widespread corruption, and weak institutions, leading to inadequate building codes and poor infrastructure that made buildings highly vulnerable to collapse. Emergency response systems were underfunded and uncoordinated, leaving the country with limited medical resources, poor transportation networks, and insufficient rescue operations. This lack of preparedness and slow response worsened casualties and hindered recovery efforts, amplifying the devastation of the earthquake. Enquiry Question 3. How successful is the management of tectonic hazards and disasters? The first part of this video will cover tectonic disaster trends. The number of recorded disasters has increased significantly since 1960. This can be seen on the graph shown. The increase in natural disasters since 1960 is due to climate change, population growth, environmental degradation, and improved disaster detection. Human activities like burning fossil fuels and deforestation lead to global warming, intensifying storms, droughts, and floods. Rapid urbanization puts more people in disaster-prone areas, while deforestation and wetland loss make landscapes more vulnerable. Advanced technology also means more disasters are detected and reported than in the past. Extreme weather events, influenced by patterns like El Niño, are becoming stronger and less predictable. Together, these factors create more frequent and severe disasters worldwide. Now let's take a look at disaster statistics. These have improved significantly but still face challenges. With advances in technology, like satellites and data collection tools, tracking and recording disasters is more accurate than ever, covering a wide range of natural events globally. However, data quality can vary between regions due to differences in resources, infrastructure, and reporting standards. Developing countries, in particular, may have underreported data due to limited monitoring capabilities. Historical data also has gaps, especially for events prior to the digital age, making long-term trends harder to assess. Politics can play a role in the reporting of statistics from disasters. We will now look at tectonic mega-disasters. Here are some characteristics of them. They are massive disasters, either in their physical size or social and economic impacts. Communities and governments require immediate aid. This can involve international loans and aid given by NGOs, such as the Red Cross. They can impact multiple countries. This can be indirectly or directly. They are infrequent but severe and cannot be fully managed to mitigate the risks. The case studies shown are important to know. Refer to my case study series for more information. Disaster hotspot is a key term to know. A disaster hotspot is a region highly vulnerable to multiple natural hazards, where environmental and human factors increase the risk of disasters. This diagram illustrates the features of a hazard hotspot and how they contribute. Once again, you can see that vulnerability is a factor. If you are unfamiliar with this, watch my Enquiry Question Two summary, where this is covered in more depth. A hazard hotspot example is Bangladesh, where frequent flooding, cyclones, and river erosion occur. Its low-lying geography and location along tropical storm paths increase its vulnerability to these natural hazards, affecting large populations regularly. Let's explore the hazard management cycle. The hazard management cycle is a process involving preparation, response, recovery, and mitigation to reduce impacts and improve resilience to disasters. This is Park's model. Park's model, also known as the disaster response curve, illustrates the phases of recovery after a disaster, showing how quality of life and stability are initially impacted, then gradually restored over time. It highlights 4 main stages: pre-disaster, normal conditions, disruption, immediate impact, recovery, efforts to restore stability, and improvement, potential development to a better state than before. The model emphasizes the variations in recovery time and resilience among communities, aiming to help understand and improve disaster response and long-term recovery strategies. Here is another diagram showing the cycle. Take a look at the diagram and notice the similarities to Park's model. It is useful to be familiar with different diagrams in case they appear in your exams. Let's look at the prediction and forecasting of earthquakes. While it is not possible to predict the exact time, location, and magnitude of an earthquake, it is possible to calculate the probability of a significant earthquake occurring in a specific area over a given time period. Here you can see the methods used. On the bottom left, you can see ground deformation monitoring. Here, instruments like GPS and interferometric synthetic aperture radar monitor changes in the Earth's crust that might indicate stress build-up. The bottom middle image shows early detection systems. These systems detect seismic waves and provide alerts seconds to minutes before the shaking reaches populated areas. The key thing to note is that earthquakes cannot be predicted early enough to warn the population and mitigate risk. The final image shows the analysis of historical data. This is useful for attempting to understand patterns in seismic activity. However, these data sets are still being analyzed and no links are known for sure. Here are 3 main methods used to predict when volcanic eruptions could occur. Unlike earthquakes, volcanic eruptions can be predicted in advance. This leads to risk mitigation through evacuations and other preparations. This was seen in the Icelandic volcanic eruption of 2024. Firstly, increased seismic activity, such as small earthquakes or tremors, often precedes an eruption. Seismometers detect these movements as magma rises toward the surface. Volcanic eruptions release gases like sulfur dioxide and carbon dioxide. Increased emissions or changes in the composition of gases can indicate rising magma and potential eruptions. You can see this being measured in the middle image. Thermal imaging can be used. Satellites and ground-based infrared sensors detect temperature changes on the volcano's surface, which can indicate increased volcanic activity or the buildup of heat from rising magma. Other methods can be used, but if you know at least these 3, you will be prepared for any potential extended answers. In this section, we'll explore strategies to modify hazard events. There are 3 stages of disaster management. These are: modifying the event, modifying the vulnerability, modifying the loss. The next sections will look at each aspect of this in more depth. Modifying the event. Features of this method include hazard avoidance using land zoning, engineering defenses, retrofitting of homes, hazard resistance design. The image below shows retrofitting. Retrofitting is the process of modifying existing buildings or systems to add new features or technology. It can be done for a variety of reasons, including to make a building more energy efficient, safer, or sustainable. Retrofitting can make a building safer by adding bracing to stiffen walls, reinforcing pillars, and installing shutters on windows. Modifying the vulnerability. Features of this method include prediction and warning, community preparedness, education to change behavior and prevent hazards becoming disasters, modifying the loss. Features of this method include giving aid to those in poverty, providing insurance to help manage property loss. This is more useful for wealthy people. Providing emergency relief to reduce loss as a result of secondary hazards. This table shows methods to modify hazard events. Earthquakes and tsunamis cannot be modified in a way to change their nature, but methods can be used to improve resilience. For example, retrofitting and construction tsunami walls. For volcanoes, lava diversion can be used. Efforts to redirect lava flows using barriers or trenches can help protect infrastructure and settlements. However, this is often difficult and costly. Ashfall management is developing techniques to manage ash, such as using water cannons to prevent ash buildup on roofs or roads, can reduce disruption during eruptions. Creating safe zones, shelters, and efficient evacuation plans ensures people can quickly move away from erupting areas. When we talk about modifying vulnerability in relation to hazard events, we are focusing on reducing the impact that these events have on people, property, and the environment. The goal of modifying vulnerability is to make communities more resilient so they can withstand and recover from hazards more effectively. One way to do this is through mitigation, building stronger infrastructure, like earthquake-resistant buildings or flood barriers. Education and awareness are also critical. Teaching people about how to prepare for disasters, such as having emergency kits, evacuation plans, and understanding warning systems, can save lives. Planning and zoning are another key strategy. Governments can regulate where to build, avoiding construction in high-risk areas like floodplains or volcanic zones. Finally, economic development plays a role. Wealthier communities generally have better access to resources for disaster preparation and recovery, so improving overall wealth and social support networks can help reduce vulnerability in the long run.